Okay, so if I click the green flag, what we get is this V-shaped thing decorated. And there's 3 different kinds of decorations: squares, hexagons, and stars. And for some reason I don't understand, the random number generator doesn't seem very random, because if you look at it for a while, you'll see more hexagons than anything else. But you get the idea. Sometimes you get things that aren't hexagons. Okay, so how does this work? Well, the script says, go to this place, show, pen down, clear, point to the right. And then, no, point up, sorry. And then run V. And let me show you the V block. It says, turn left 45, move 25 steps up, and then choose a random item from that shapes list and run it. So this part is kind of a preview of things you'll see later, because what's in that list is blocks. So we have the ability to treat little chunks of Scratch programs as data. And in particular, we can make a list of them. And we can choose a random item out of that list and run it. And that's what this run thing says. So come up here, run either square, hexagon, or star. Then come back down where we were, turn right 90 degrees, move forward 25. Now we're on the right branch. And then again, pick a random shape and run it. And then come back down and then turn left so that we're facing back the way we were when we started. So the sprite ends up in the same position and the same heading as it was when it started out. Okay. So now what I want to do is I'm going to modify this shapes list a little by adding V to the list. V is the block you just saw that draws this whole thing. And so the question is, after adding V to the shape list, clicking the green flag will draw A, same as before. B, maybe the same as before, or maybe a V with a little v at the end. C, same as before, or a whole other V at the end. Same as before, or 2 double V's, or something completely different. Now I have to do what? I have to turn on this thing. Wait. Hello? Start polling? Maybe I'm.
Did you run the program? Did you like actually run it?
I have to run the program. Okay, hang on. Sorry. Where is the program? It's in my computer. Sorry, I'm not good at clickers. Oh, here we go. Kingston. Clicker window. Web update. No, grader.exe, iClicker.exe.
Right. And then you should choose the class.
Yep. Once it starts running. Once it starts running, I can choose the class, of which there's only one.
You say start, I think, the circle in the middle, click, yeah.
Yeah, I click start session.
And now, when you do it.
And now, let's put the question back. Hang on. There we go. Okay. All right. So wait, if I go here. What? No, wrong thing. Cancel. That's what I meant to push. Okay. Start. Okay. Winning away.
It's in waiting mode.
It's in waiting mode. Oh, going. Okay. Come on, there's more of you than this. Maybe there's not. Okay, fine, I'll take it. Done. Display. Interesting. Should we show the correct answer? No. Let's just, okay, yeah, sure. Okay, so some people think it'll stay the same. Hardly anybody thinks it'll have a little v. Most of you think you'll get a double V or maybe two double Vs, and 6 people think you get something else. Well, I'm just going to do it. Huh. That's something else. Double, that's like a triple V on one side. Whoa, there you go. Okay, you guys who said 6, is that what you were expecting? Said E, I mean, is that what you were expecting? There's 6 of you who said E. Anyway, okay. Wow, how does that happen? Well, what? Oh, yeah, sure, I can. But I'd rather just move it over. There. Okay. So let's look at V again. It says, turn left, go up, and pick a random one of these shapes. So let's say it says V. And by the way, why did I put V in the list twice? Well, I just discovered by putzing around that that made this kind of picture pretty likely, without making it go on forever, ever. So it picks one of these, and 3/5 of the time, it just draws a hexagon or a square or a star. But 2/5 of the time, it calls V. It does this block again. So here's my sprite. Let's look at how it did up to the right. So it's here, and it says, draw a V. OK, so I'm going to draw this V. Well, I'm on the left branch of the V. What should I do? Oh, draw a V. OK, so I'm on this V, left branch. What should I do? Oh, draw a V. Well, the left branch is a star. How about the right branch? Oh, a V. OK. So this could go on indefinitely. Could it go on indefinitely? Could it really go on forever and never stop? What do you think? Who says yes? Who says no? Oh, come on. Be brave. Who says yes? Who says no? OK. Somebody who thinks no, why not? Why couldn't it go on forever? Yeah. Yeah, OK. That's pretty subtle. Yes, I think that's absolutely right. That in principle, it could go on forever. But the probability of seeing even a second V is only 2/5. The probability of seeing a third V is 2/5 of 2/5, which is less than 2/5. Right? It's 4/25. The probability of seeing a fourth V is 2/5 of 2/5 of 2/5. So as the number of V's goes on, the probability gets lower and lower and lower. And the probability of seeing infinity V's turns out to be 0. So it really isn't going to happen, even though in principle it could. OK? Well, what this is a very roundabout way of having the block V call itself V. It doesn't do it by dragging a V into here. It does it by this run, picking an item randomly out of this list, and sometimes the thing it picks is V. Something calling itself is called recursion. Okay, and that's the topic in lab for the next 3 weeks, alternating with you working on projects. And also, we're going to have lectures about recursion once a week for the next 3 weeks. Because it's a big idea. It takes a while. There's not that much to say about it. In a certain sense, we've said already about 9/10 of what there is to say about recursion, which is a procedure can call itself. And all the rest is details. As you can see, it's an incredibly powerful technique. So we have this tiny little program. And when you don't have V in that list, the program does something really trivial. And just adding the possibility of recursion allows a small script to generate this very, very complicated process with the sprite just running all around the screen. And by the way, finally ending up exactly where it started. So one of the things we're going to be talking about is why doesn't it get lost? And that's an important thing to understand about recursion. But it's going to take a while for this all to sink in. You're going to have to sleep on it a bit. And that's why we spread it out over sort of half the time for 3 weeks instead of cramming it all in. Because I could say it in a week, but you wouldn't, if you're new to recursion, it would take longer than that for you to really absorb and be able to use the idea. So we spread it out. Okay. So let me answer the question I just raised. Why doesn't it get lost? So we're doing a V, and we're up here, and we say, oh, let's go left, and let's go left again, and let's go left again, and draw a star, and right, and left, and back. It's very, very important that the script leaves the sprite in the same position and heading that it started. So when I'm, let's say, right here, can you see that arrow? I'm right here, and I say make a V. And I'm pointing, by the way, out this line, straight this way. So I say make a V, so we turn left 45, come back, right 45, draw a V. We have to end up right back here, so I can say left 45, and then retrace my steps back down here to be in the right place to draw this. So these last couple of steps, after you've drawn everything, this move minus 25 steps, turn left 45 degrees, doesn't actually add anything to the picture. It's just retracing its steps. But it's important so that calling V leaves the sprite where it found it. Otherwise, it would get lost. Might even be worth demonstrating. What? Really, it'll just go away?
If you close the block editor, it'll disappear.
All right, I can fix that. See, it got lost. It was supposed to come back down to here, but it didn't. So this idea here of bringing the sprite back to the same position and heading where it started is called state invariance, because the position and heading is the state of the sprite. It's sort of what it remembers about where it is and what it's doing. There's more to this state, too, like whether its pen is down or not. But the most important parts are the position and heading, meaning what angle is it facing. OK, so that's number one. Thing number two is what if instead of having it be random like this, I would like to be able to control the depth of V-ness. So, oh, be quiet. I want to be able to say, I want 3 layers of V, a V, and then V's over here, and then V's over here, and that's it. Okay? What? On every one, yeah. So we're going to have to change this program a little bit to make that happen. And what I'm going to do is duplicate this script and drag it down here for a moment. So I'm going to make it take an input called depth, which says how much deeper than it is now should the V go. And I'm going to drag this script in here. But I'm going to take V out of the list, and I'm going to change this run thing. It's going to say, if the depth is 0, then pick a random shape out of the list. If the depth is non-zero, then I'm going to call V. So I'm going to be sure to call V, and I'm going to give it a smaller depth. So let me go ahead and draw that. Forgetting how this works. If depth is equal to 0, then pick a random shape. Otherwise, hey, thank you. Yeah, I know. It's very annoying. OK, so just look at this for a minute. So if we come in here and depth equals 0, we turn left, move up, depth equals 0, so I do a star or a square or a hexagon. And then I'm going to come back down and so on. So that's depth equals 0. If depth equals 3, I turn left, come out here, and call V with depth equals 2. Well, what if depth equals 2? I draw a V of depth equals 1. Depth equals 1, I draw a V of depth equals 0. And that one doesn't call V, it just draws the shape again. So let me duplicate this, put it down here. No. Yeah. Oops. And now, V of depth 3. See what this looks like. OK? So that's a nice symmetrical. Here's the first V. This is a V of depth 2. And this is a V of depth 1. And this is a V of depth 0. So just to make sure you understand the point, here's a V of depth 0. That's the thing that we started with. It always just draws a simple thing. If I say V of depth 1, then the big V has a V in each branch, and those little V's have star square hexagon at the ends. Okay, so that's depth 1. Here's depth 2. Three, and so on. Okay, let me stop for questions. Yes? 4. Sure. Maybe. Looks like that. Anything else? Okay, so looking at the code again. This test for depth equals 0, this is called a base case. In the original version of V, there is no explicit base case check, and that's because there really is a base case, but it's probabilistic. We're going to choose whether or not to do recursive call, and we're going to do it 2 times out of 5. So eventually we hit a base case that way. But here we have a controlled base case where we're actually testing an extra variable called depth that controls how many levels of recursion to have. If I come in to V with depth equals 3, and right here it says V of depth minus 1, does that change the value of depth from 3 to 2? We should make this a clicker question, huh? Okay, clicker question. Yeah. So the question is, right here, we came in V of depth 3, and here we say V of depth 2. Is the effect of that to change the value of the variable depth from 3 to 2? Yes, click A, no, click B. Oh, yeah, so I can. Yeah. Okay, good enough. Somebody thinks C, all right. Well, 2/3 of you think no, which is the correct answer. It does something different from that. What it does is it starts a whole new, here's the way to think about it. Inside your computer, if you continue the study of computer science in 3 more semesters in CS61C, you get to learn what's inside the computer. But I'm going to tell you right now, inside the computer there are a lot of little people. And each little person knows how to run a particular block. So there are people who know how to run the move so many steps block, and there are people who know how to run the if else block, and so on. And in particular, there are a bunch of little people who know how to run V of depth. So when right out here we say v of depth 4, what we're doing is we're hiring a little person named Victor. And he has a pocket labeled depth, and in his pocket is a piece of paper that says 4. Now, Victor comes down here. He looks at depth. It's 4, so it's not 0. So, oh, I have to do v of depth 3. So Victor hires Veronica, who's a little person who knows how to do v of depth, and puts 3 in her pocket. Now, Veronica turns and moves and says, oh, depth is 3, it's not 0. Oh, I have to do a v of depth 2. And Veronica hires what? Okay. What he said. And he has depth equals 2. He comes down here, oh, I have to do v of depth 1, so I'm going to hire Victoria with depth equals 1, and Victoria says, I'm going to hire Venkat with depth equals 0. Now Venkat comes down here and says, oh, depth equals 0, so I'm going to draw a star, a square, or a hexagon, and so on. Finally, Venkat comes all the way down here and finishes, says, okay, I'm done, to the person who hired him, which is Victoria. Victoria's depth is still 1, the same as it always was. It's not that we change the value of depth. We're making a new little person with a new pocket with the same name and a different value in it. When that little person finishes, the old little person still remembers depth equals 1, comes down, finishes, goes back to the v person whose name I forget, who has depth equals 2, and so on. Okay? So that's how computers really work. It actually is. Little people inside. Each little person has its own set of local variables for the inputs to the procedure, in this case, depth. So there's no changing of the values. It's making a new variable with the same name belonging to a different person. Okay? It's really, really important that you think of it that way. Even though you think it's silly, because, you think there aren't little people inside the computer. It's very, very important that you think about it. That's the right way to think about it. Otherwise, what some people end up doing is they end up thinking, oh, change the value of depth and then go back and start over again. Anytime you find yourself thinking a sentence that has go and back in it, it's wrong. Okay? Just, no, not go back. It's not what happens. New little person. And that's important because after this, we have to continue with the rest of this procedure, and we have to do it with the correct value of depth. Otherwise, things will get all messed up. Okay?
Making a list of poly things, and at the beginning of it say add column v of depth number.
Oh, you want me to trace it?
Yeah, a manual trace, just the start and the end of it. On the left.
Okay.
Shapes, make a new list.
Okay, make a new list. All right, let's do that.
Hold the list.
Make a list. We'll call it trace. Okay. So right up here, we're going to say add join var of depth to shape, to not shapes, to trace. And what? Var v. Sorry, I'm not totally awake yet. And then at the end, no. Why do I want to? Oh, you want me to? Oh, you want to? Oh, I see. I was just going to have them. Let's do it my way, and then we'll do it your way. Okay, so we're going to make this box a little bigger. You think? Okay. Okay, here goes nothing. Yeah. Isn't that cool? Here, we'll do it again. So much fun. So look at the numbers. It's 4, 3, 2, 1, 0, right? So depth equals n equals depth equals n minus 1. It's so much fun. Can't stop watching this. Sorry? No, there aren't any stacks. This is a language with lexical scope and lambda. So there's no stack. Okay, never mind. We're just having a little side conversation. Okay. So recursion is a procedure calling itself. Using recursion, we can do complicated things in simple manners. No. There we go. Okay. Oops. I should have done this ahead of time, but as usual, I was in a big rush getting ready for class. Okay, so if we have a word of length 1, then we just output the word. Otherwise, oh, I don't have but first. Oh, I have to, okay, never mind. Let me import. What? I'm going to show them what DownUp is doing, and then I'm going to. Oops. Sorry. I don't know why this is so slow. We're gonna fix this. Make it blindingly fast.
What's the advantage of recursion over loops? Like multiple loops?
Good question. So, all right, let me answer that by going back to this picture. Okay, imagine drawing this as a loop. Okay, turn left, go forward. Now what? Go back to the beginning. Okay, you're going to go left, 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 and you can do that and control the number of times equaling to depth. That you go left, 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 but now you're out of luck because you've forgotten where you are. So when depth, let's put it this way. When depth equals 4, how many, not counting the little shapes at the end, how many line segments does it draw? Well, for depth equals 0, how many line segments does it draw? 2. For depth equals 1, how many does it draw? 6. For depth equals 2, how many does it draw? 14. For depth equals 3, how many does it draw? It's 14 and 16, right? It's 30. So that's a bigger loop than you're thinking. And you can't really, you know, when I'm drawing line segment number 15, where am I? So I'm not saying it couldn't be done with a loop, but when you have a structure that branches out like this, recursion is just such a natural way to think about it, and looping is such an unnatural way to think about it, that if you try to do it iteratively, you're going to make mistakes, guaranteed. If you try to do it recursively, it'll work the first time, after you've been doing recursion for a week or two.
You can still do it, you just have to keep track of a lot more stuff. So there's nothing more powerful about recursion, just simpler. Just keep track of where you are.
Yeah.
Simpler depending on the question. Simpler for this particular problem.
Well, simpler for any problem that branches, right?
Okay, right.
And I would say as simple for other problems. Okay, so do I have down up here? Let's, okay, here we go. So now I can do this the right way because I have join words. Yeah, but nevertheless. Okay, word. And then down up of all but last letter of word. And then word. Okay? We're going to come back to this program in a minute after I show you what it does. Say down, up, hello. This is my favorite example in the whole world. Okay? This is what down, up does. It sort of goes down and back up again. And while that's up there, let's look at the down, up program. So this is a recursive procedure, and the base case is length of word equals 1. So I have the word, for example, H, in which case I just report H. If length of word is bigger than 1, then I take the whole word, like hello, and then down up of hell, which is all this stuff in the middle, and then hello again. Okay? So again, this is definitely something that you could do with an iteration. But why would you want to when you can express it in this very, very compact way that is hard to read when you've only just seen recursion for the first time today, but I promise you is going to get to be very easy to read. So I should back up a minute and say this is a course about big ideas. And some of the big ideas are sort of technical, programming big ideas. And some of the big ideas are, you know, what computers are good for, or what computers can't do, or things about the use of computers in society. Recursion is maybe the biggest big idea about programming that you're going to see in this class and that you're going to see, period. This is like the central big idea, one of two actually big ideas. The other one is coming up near the end of the class, and it's the thing that you saw a little preview of, where we can take a bunch of Scratch code. We can take a script or a block of Scratch and use it as data. And that turns out also to be an amazingly powerful idea. But recursion is the one you're going to be focusing on for the next few weeks. And it is really the central, you know, separate the serious computer scientists from the dabblers idea. So if you go out in the world and get a job as a computer programmer, you will meet people who are afraid of recursion. You will meet people who say, oh, recursion, that's inefficient, or something. And the difference between you and them is that your programs are going to work the first time, and they're going to be still writing the same program a month later. It's really that crucial an idea. So, recursion, big idea. We have 5 minutes. I think I've said everything. Any questions?
Any examples of recursion in the real world outside of computer science?
Oh, recursion in the real world outside of computer science. Yeah. There are certainly examples of self-reference in the real world outside of computer science. Fractals, you know, but that's
We're going to see a lot of images in lab today.
yeah, are you? Okay.
Visual.
Yeah, right. But those grow out of computer programs. I want to know if there's an example of recursion that's just totally not. Yeah. Oh, thank you. Yes. Thank you. That's the best. So you have two mirrors back to back, like at the clothing store, where there's those ones that swing out, right? And if you're only swung out a little bit, you see like yourself from the left and yourself from the right. But if you get them so that they're parallel, you see a bazillion of yourself getting smaller and smaller forever, right? That's recursion. It's a reflection of a reflection of a reflection of a reflection in the two mirrors. Thank you so much. Great example.
Can you talk about the running time Taylor off adjusting of the tree?
The running time, well, we talked about how many line segments there are. And the number of line segments roughly doubles with the depth. And so the running time roughly doubles with the depth. So it's exponential time. So if I were to do a V of depth 8, we'd be sitting here for a good long while. We'd get there. I mean, if I'd started it at the beginning of class, it would be finished by now, but it would take a while. But having said that, I want to clarify, emphasize that that's not recursion's fault. It's the fact that we're drawing a picture with 2 to the 8th lines in it, and no matter how you slice it, that's going to take 2 to the 8th amount of time. Okay? So it's the fault of the complexity of the problem you're trying to solve that makes the running time what it is. So, okay, the big idea is here. Recursion is a procedure calling itself. In order to make recursion work, we have to have a base case. There has to be some situation in which the procedure doesn't call itself recursively, but instead does some simple thing. And the recursive calls have to be getting us closer to the base case. So when I said in the v of depth program, use depth -1 as the input, if I had said depth +1, so for a v of depth 3, we drew two v of depth 4s, right? V's of depth 4. And then for each of those, we draw two v's of depth 5. We'd be getting further away from the base case, and it really would run forever without stopping. So the recursive call has to be getting us closer to a situation in which we can run without recursion, and that's the base case. So recursion itself is one important idea. Base cases is the other important takeaway idea from this. I'm going to put this on the web page as soon as, well, this afternoon. Okay? Thank you.